All right. Yeah. Thank you very much. And thank you for the opportunity to talk to your Google developer groups. I gave a talk last week at Developer Week in San Francisco about real-time access to big data, and I just made some changes to that talk to have more of a basic introduction to Hadoop for Java programmers. I can't really see a show of hands, but I'm guessing a fair number of people in the audience are Java developers, and hopefully you'll be able to follow some of the code as I give an introduction to MapReduce. So the talk was titled "The Year of Real-Time Access to Big Data," because there are a whole bunch of technologies coming down the pike for Hadoop that are geared towards making Hadoop more interactive in real time. This talk includes a survey of what those access methods are. But for beginners, what everybody wants to know about is basically Hadoop, MapReduce on Hadoop. And MapReduce is sort of the slow way of doing data science, but it's very well understood and it's very effective. So I'll talk quite a bit about that in this talk. So let's go to slide 2.
Okay. Yeah, we are on slide 2.
So great. Yeah, so the agenda for the talk is some introduction to MapReduce, basically how do you write MapReduce code. Then we'll talk about how MapReduce fits into the Hadoop stack, because Hadoop actually consists of a couple different layers. And since the gist of the talk is to talk about real-time, we have to talk about how real-time the Hadoop file system is. And then we're going to talk about some of the methods that have been built on top of Hadoop, like HBase, for doing key-based indexing. And then we're going to get into a little bit of the layers of Hive and Pig, and some of the things called MPP, massively parallel processing approaches, which include some things that were invented at Google, like the Dremel architecture, and talk a little bit about Spark, which is an alternative to MapReduce. Okay, so let's go to slide 3.
Okay, we are.
Oh, and I should say, if you have questions at any time, just feel free to, maybe you can tell the presenter to ask me so I can hear you. Then I can answer your question. Okay, so here's a diagram of MapReduce that I don't think is a very good diagram, but I included it because it's the diagram that's shown on the wiki page for MapReduce, and I figure that's probably one of the first places everybody goes to learn about MapReduce if they don't know about it. So I wanted to just comment on this diagram a little bit. This is more of a conceptual diagram of MapReduce, and MapReduce is a technique for parallelizing the code for implementing algorithms, but the thing that most people don't get their head around when they're trying to figure out, should I use MapReduce, is that one of the biggest things that MapReduce does is give you this sort of global paradigm of a distributed hash map. It's not just that you have these parallel pieces of code, it's that you have these parallel pieces of code that operate on the input and then shuffle the data around in a global way. And so to me, this diagram looks like you have worker nodes and all of the data is flowing through a master node. And that's why I don't think this diagram is a good picture of MapReduce. And then if we go to slide 4, I think we can find a better, more detailed picture of MapReduce, which shows you what's actually going on. Okay, so at the highest level, the reason MapReduce is called MapReduce is because you have a first phase that starts with an input, splits the input files that are in HDFS up on certain boundaries, and then allows your code to essentially put keys and values into a global hash map. And the place in the middle of this slide, and in a minute I'll talk about what this algorithm is doing, this word counting algorithm. But the place in the middle of the slide where you see all the arrows sort of going in all the different directions, that's the phase where MapReduce is doing its global shuffling of data, which happens through the distributed file system in HDFS. So the map phase of MapReduce allows you to take data from the input and emitted into a global hash map as a key and a value. And then the reduce phase of MapReduce, and I've circled one of the reducers and we'll dig into it and look at it, allows you to operate on a list of values associated with that key. So you can kind of think of MapReduce as being this global hash map where you have keys and then you actually have lists. So when you write something out as a key and a value, in a global sense, what you're doing is appending a value into a global list for a key. And then you have code in the reduce phase that can operate on that global list, okay? So what this example is trying to demonstrate is a simple counting of words. So you have a file full of words, deer, bear, river, car, river, deer, car, bear. And then all the way on the other side, on the final result, we've counted up those values. There are 2 bears, 3 cars, 2 deers, and 2 rivers. And so then let's look at how the files get split up. So in the first phase. So one of the neat things that Hadoop does for you with MapReduce is manage the sort of decomposition of a giant file in HDFS, which maybe it's a terabyte, doesn't matter how big it is. It manages automatically locating what are called the splits for that file. So it's something you as a programmer don't have to worry about. You have a giant file, it's in HDFS. Hadoop takes care of identifying the split boundaries for the file and telling individual mappers, right? Because it's parallel processing, so you have a bunch of different mappers running on different computers in your Hadoop cluster. And it tells each of the mappers where the split boundary starts and where the split boundary ends. So in this example, there are 3 splits that MapReduce has identified in the big HDFS input file. And so the 3 splits consist of, one of them has deer, bear, and river, one of them has car, river, and the other has deer, car, bear. So your mapper, in this example, the piece of code that you write is automatically going to be invoked on each machine. And it's going to be invoked one time for each word, basically, in this model coming into the mapper. And what your code is doing is emitting in the map phase the value, and then it's emitting a number. So it's emitting, and it's doing something kind of dumb, but it's a typical example, is that it just emits the word 1, the number 1 for each instance. And then the reducer basically just sums up all of the numbers 1. So however many there are, it adds them together and produces the sum. Now you might think, why would you do that, where it just emits the number 1? That seems kind of silly, but what's not shown here is that reducers can actually be pushed into a variety of different places inside the process of shuffling. And when you do that in Hadoop, it's called a combiner. And so if you have combiners in place, when you get to the reducer, your reducer list might not be just a list of the numbers 1. You might have had several combiners invoked in different places, and so you might have the number 1, but then you might also have had a reducer acting a combiner that added several of the number 1s together, and so maybe you have 1, 1, 5, 3. Hadoop doesn't give you any guarantee about whether a combiner will be invoked or how often it will be invoked, so you have to be kind of careful about using combiners. But be aware that in a lot of algorithms where you're doing things like summing, if you can basically cascade reducers using combiners. Okay, let's get into a little, and any questions?
Yeah, I'm sorry, but you have shared a new document and I don't have access to it, so we're not seeing the slides yet.
Gotcha, okay, I'm giving you access now. Let's wait a second, it's got to come back up here. Okay, let's see, do you have access now?
Seems so. Just a second.
Yeah.
Yep.
Okay.
Yes. And we're on slide 4.
We'll go to slide 5, unless anybody has questions about the mechanics of that example. Okay, so slide 5, basically, now we're into a little bit of code. And this is just an example of word count that's available on the Hadoop Wiki, Apache Hadoop Wiki. What you're going to do when you fire off a MapReduce job, basically how do you do it, is you have to have some code that communicates with the orchestration framework, if you will, of MapReduce to tell it where your data is, to tell it what the types are that you're emitting from each phase, and to add to the confusion, Hadoop has gone through a couple different cycles of its APIs, and to a large extent, they didn't make substantive changes. They just made, as a programmer, a lot of times you look at it and go, okay, job is called job conf now, but basically it does the same thing. So this is the old style API, but it works and it's available on Amazon Elastic MapReduce, and some of the things like multiple outputs weren't working in the new APIs, so all the books that you get are going to pretty much stick to the if you will, the old API. So this is it. So the first thing that you have to do is basically create the notion of a job, which you give a name to. Then you have to tell the job, and it doesn't matter what order you do these things. It might make sense to actually first tell the, just from a readability point of view, tell the job what the input format is. But I'll stick with this code as written. So what they're going to do first is tell you what the output type is, and so outputs from Hadoop can have different formats, but they are typically key value formats. So in the word count example, you would imagine your output has to include the word, and then it has to include the count of the number of occurrences of that word globally. So Hadoop has something called writables, and anytime you need to move data as an output from the mapper, as an output from the reducer, meaning the job output as an input to the job, the types that you use, they can't just be regular old Java primitives like a long, or an immutable string. They have to implement the writable interface because Hadoop needs to sort of squirt them around the network. So for text, you use, instead of string, you use text, which implements writable, and for use int writable, etc. It's pretty basic, but it only provides you with primitives, of course, because if you want a more complex object, it's up to you to design that and implement writable, and we'll talk about that in a bit. So yeah, so the output from the word count example is, of course, the text for the word and a number that represents the global count. Then you've got to tell Hadoop what classes it should actually use for your mapper and reducer. So in the next slide, I'll show you the map class and the reduce class, but those are the custom classes written to implement this type of word counting. Then you have to tell the job what format the input is. And sequence files and map files, once you get into it, and I'll describe what those are tend to be more typical than just using text. The text is kind of not a very rigorous way to pass values around. So it's okay for an example, but in reality, once you get into things, you're going to be using sequence files and map files. But the input to this is basically just a text file, and the output is a text file. But then you're probably thinking to yourself, well, what does it mean when I output the key and a value, but the result is just a giant text file? So like I said, text output format is kind of a silly format, and it just takes the key and the value and separates them by a tab and then puts a new line at the end. So it kind of takes keys and values and just turns them into a CSV file, if you will, or a TSV file. Okay, so finally you got to tell Hadoop actually where in the file system your input is coming from, and that's going to be typically a path in HDFS, and you got to tell Hadoop where to put the result of the job when you're done. And those two things, in the case of this program, are passed in as arguments to the main. So what that argument might actually look like is, the first argument to the main might be a string that was HDFS : / and then the server name of the name node in HDFS. I'll get into that later, but HDFS is a distributed file system, and you represent data as URLs, and the URLs include the protocol, which could be, as you know, the Hadoop file system can accommodate things like S3 as the protocol. It can accommodate HDFS. So you include the server identity, the port that the name node is running on, and then from there it looks like a regular URL. My data / text / input.txt, but input.txt could be a 100 gigabyte file spread across many machines. And then finally you invoke wait for completion on the job, and when the job is done, that method will return, and you should go look in your folder in HDFS and find a bunch of files that represent the output. Any questions on slide 5? Okay, slide 6 then. So, let's see, you may have to scroll the slide over a little bit to the left to actually see the beginning of the method. I don't know if the presenter can sort of slide it over to the left, because the text was a little bit too big to fit down.
Yeah, but now we can't see it. I will just go to left and right.
Yeah. So basically, you're going to implement a class that extends this base mapper. And you're going to see that the mapper has 4 types. And those are the types of the input key, the input value, the output key from the mapper, and the output value from the mapper. And you might be thinking to yourself, wait, if this was a text file, what is the input key? I mean, the input value, I would assume, if you're looking at this new, you would take a guess that that is the actual text of the line of the input file, and you'd be right. But what is this long writable? That's the first type defined in the map class. And it's actually the byte offset into the HDFS file where that line began. And most of the time, you don't actually have to use that for anything in the case of text input files, text input format. And as we'll take a look down at the map method, and you'll basically see it's not used for anything. But what is used for something is the value. And what they're going to do here is, just like in that diagram I showed before where they omitted 1, they're going to take a Hadoop writable object called the text. The name of the variable is word, and they're going to set the token into it, and then they're going to emit it using the context write method with a key that is the word and the value that is 1. And I think as a developer, I mean, I look at this code and I just think it's kind of strange that there's something like a statically defined variable called 1 that they're going to be using over and over and over again. But if you think about it, these methods are going to get invoked a number of times, a huge number of times. And everywhere in Hadoop you'll find code like this where the thinking is, how do I avoid allocating objects? So all that's going to happen when context.write gets called is the int writable 1 is just going to get serialized over and over and over again. And in this case, it's never changing. So they're simply making the point that they don't have to allocate memory over and over and over again to do that. If we go to the next slide. Oh, and let me just say, like, one of the cool things about MapReduce is, I should have said this earlier, you basically are, as a programmer, your lifestyle involves implementing just, for the most part, 2 methods, map and reduce. And that's really the nice thing that MapReduce does, is it takes care of pushing values into your methods versus forcing you to go out into the world of input files and parse the values and find them. So it does all that for you, which is one of the big advantages of working. Okay, so now we can go to slide 7, and again, maybe we can scroll over to the left and take a look at the reduce method. So reduce, remember when I was saying that MapReduce gives you this paradigm of a global hash map, and every time you write out a key and a value, what you're doing is actually adding the value to a global list corresponding to that key. And so in the reduce method, you're going to get that key. That's the text, right? That was the word that you were counting on. And now you're going to get an iterable over all of those number ones, or if you had a combiner in place, like I said, it could be summed up intermediate values. So almost always what you see in a reducer is you're iterating over that global value list, and you are somehow, why they call it reduce, because you're doing some sort of a reduction on the value. And so instead of keeping this whole list, you just add up the numbers to the sum value. And what is val.get? So why can't I just sort of be adding sum plus equals, val? Well, again, int writables are Hadoop writable types. They're not primitives, and to sort of extract the value of the long out of the int out of the writable, you have to call get on it. Then when you're done iterating over all the values, you now can write the value into the output. And so you're going to be writing the key and creating a new int writable that holds the sum. And this is a very straightforward example, but I have the next slide when we go to slide 8 that's going to give you some warnings about iterating in reducer groups. And so when you talk about all of the values in the list associated with a key, that's a reducer group. And then what I'm showing in the little picture on slide 8 is, the reducer group for var in our example is actually a list with 2 ones in it, and your code is going to iterate over it, and it's going to emit var and the sum of the 2 ones. Okay. The following point does not get enough coverage in Hadoop books, and I think every Hadoop book or tutorial should have a big, giant red page in it that says, never forget this. When Hadoop gives you an iterator over the values in the reducer group, it reuses the same object every single time. And again, this is back to avoiding allocation of objects to be nice to the garbage collector. So if you were to compare the current value in your iterator using equals to the previous value in your iterator, you would find that it is literally the same object. But the content of the object is going to change. And that's because Hadoop is basically reusing this object and deserializing and serializing the values in and out of this object. And what happens from time to time when you're writing reducer code or combiner code is you may find yourself aggregating objects together. That is to say, making a more complex object that did something like held a reference to a nested object, and maybe in a nested object you wanted to use the object from the Hadoop iterator. The problem with this is the values inside of that object are going to potentially be changing before you emit your object. And so you can get into these bugs where the values that you've written out are actually stale. And one of the most common places where this happens is if your object has something like a list and you don't clear that list before you populate it with values from the iterator, and you don't clone the values from the iterator. And when that happens, you'll get stale state, and you'll have values in your object that don't make sense and are coming from the previous invocation of the iterator. So actually, just be very, very, think twice about any time you're emitting values in Hadoop that are non-primitive. Because that's where you accrue state, and state can get stale if you're not very, very careful with cloning the objects that come from the arrays. Okay. Stop me at any time if you have questions. So going to slide 9. How do you actually create your own custom type in Hadoop to use instead of these primitives like int writable? So you have to implement an interface called writable, and the write method is going to take values from your object and emit them to the data output interface. And you can emit strings with write UTF, it's UTF strings. You can emit bytes, you can, any primitive type you can emit here. So it's up to you to essentially marshal and unmarshal your object, and this is another place very bug prone in Hadoop. And you read the fields in the same order that you wrote them back, If you change the order, if I reversed the read order so that column was being populated before string, you would most likely get an IO exception because the format of the UTF string would have been corrupted because it's basically reading values out of the wrong place. So you have to be careful to read and write things in the same order. Okay. Now, another thing that you have to deal with is how do you control the sort ordering, the global sort ordering of keys, if you're not using the Hadoop primitive types. For example, if what you were doing was making some sort of inverted index and you were pushing documents through MapReduce, you'd have to define some sort of non-primitive object for those documents and probably some sort of non-primitive key. You have to be really careful that the compare to method, which is what controls the ordering of your keys, is consistent with equals and hash code. And if it's not, all sorts of chaos will break out and unexpected behaviors are going to happen within the shuffling and sorting of your keys in MapReduce. So the other thing that you want to be aware of is that Hadoop does include the ability to define your own partitioning of the data. But default partitioning, and what we mean by partitioning is which reducers receive which keys. The default partitioning is basically let me see how to describe this accurately. It's basically just based on essentially randomization as to which reducer gets which key. If you do, there's another type of partitioning called total order partitioning, which specifies the partition points. And if you do that, then you can add, let's say, an alphabetical partition, where if you had 2 reducers, you could decide that the first reducer received keys that started with A through, L, and that the second reducer received keys that started with M through Z. Okay. Here's an example of a partition that would make sure that all documents, or that the documents with a particular ID went to a particular reducer. So you just, in this case, I'm just grabbing an ID number, moduloing it by the number of reducers, and then I'll be sure that the documents with the same ID wind up with the same reducer. It's kind of a silly example, but I just wanted to throw out that custom partitioning is an important thing to understand in Hadoop, and you can use it. That's not hard to do. Okay. Go to slide 11. And there we go. Hadoop has 2 of its, it has a couple, but the most important, I would say, file formats that Hadoop actually has are sequence files and map files. And this is a file format, call it an application level file format that Hadoop implements on top of HDFS. It's not per se part of HDFS. And the keys and values are represented explicitly in the file. And Hadoop actually puts things called sync markers into the file so that application code, and in particular Hadoop internal code of Hadoop, when it splits your file, can find the beginning of object records. So embedded, after the values, every so often are these sync markers. You don't have to worry about them. They're pretty much hidden from you, but there are APIs to find them if you're interested. The second file format is called a map file in Hadoop. And a map file provides you with a primitive index on top of the sequence file. So what a map file does is, for every n keys, and you decide what n is, the default is, I think, 100. So for every 100 keys, the index file, which is itself a sequence file, will contain the key and the second number, which here in this slide, which I grabbed off of, I didn't write this slide, and I want to actually, now I'm noticing. To me, this looks like it's not represented accurately. The index file is a sequence of keys and values, and the value in the index file is going to be a long byte offset that points into the data file. And when you open a map file in Hadoop, it reads the index file into memory. And when you ask the map file to go to a particular key, it performs a binary search in memory to find the key. And then the corresponding value in that sequence file that's been read into memory points to the long offset in the data file, which is then automatically seeked to by the code inside of the map file. So you don't have to manage the finding the key in the index and seeking to the place in the file. The map file reader gives you an API that just says, go to this key, give me the next greater key. And then from that point on, you can begin reading values. And I think this is interesting because it means that at a very primitive level, the folks who designed the Hadoop sequence file and map file format were thinking about random access, and that it would be a natural thing for people to want to jump to a particular key and find a value. It's a very primitive form of visibility into the file structure. Later on, I'm going to get to why it's actually not a practical mechanism to manage, you can't treat it like a key value database, why it doesn't scale that way, and I'll get to that. Going to slide 12. Now, so we've done some basic introduction, well, maybe a little more than basic introduction to MapReduce. Try to give you a sense for what the code looks like, how you kick off a job, but I haven't talked about where MapReduce fits into the Hadoop stack. And underneath everything in the Hadoop stack, on slide 12, the green layer here is HDFS. So all of these layers on top of HDFS, even if it's up at HBase, their data is ultimately stored in HDFS as sequence files or map files. And you see that MapReduce is basically just an application. It's an application that has its own servers, but it's just an application that uses HDFS Hadoop file system API calls to get data out of the file system. Then it has its own code to shuffle and sort and provide you APIs for MapReduce. But then it just uses Hadoop APIs, HDFS APIs to write data back into HDFS. So on slide 13, we get into a little bit of, what is HDFS? What is a distributed file system? I want to spend a little bit of time on this because when I started programming with Hadoop, and that was like about 4 years ago, I wasn't sure where to start in my learning. And there are many different books out there. And it was just so confusing to me about how does this entire system work. And everybody wants to know about MapReduce first. And like even in this presentation, you know, I kind of moved MapReduce to the beginning because that's what everybody wants to learn about first. But to me, maybe even much more interesting than MapReduce is HDFS that underpins everything. You wouldn't have MapReduce without, you wouldn't have it working well without a distributed file system. So the implementation of HDFS involves what's called a name node. And a name node keeps track of, well, let me stop for a minute and just say another very confusing thing about learning Hadoop is, in my opinion, everything in it is named terribly. Like, to me, name node is a terrible name for something that could be called something like, you know, file system master or something like that. And all of the, in my opinion, all of the configuration files in Hadoop also have horribly confusing names. One of the key configuration files in Hadoop is called core site. And as a beginner learning this stuff, you go, site? What site? Am I configuring a website? I just found the entire naming convention system in Hadoop to be very, very poor. But anyway, the file system master, if you will, the thing that holds the metadata about where all the other files are, is called the name node. And the name node keeps track of where the blocks of an individual file are, what servers they're actually resident on, and every block in HDFS would typically be replicated with a default replication factor of 3. And when you want to locate a file, you do not think about which portion of the file you need to access or which machine it's on, because you're given an HDFS client API. The client API looks very simple. You basically open a URI, and that URI would be something like, you know, HDFS : and then the IP address of the name node and the name of the name node, and then, you know, my data / bigfile.txt. And that metaphor of being able to treat huge amounts of data that's replicated and spread across many machines as a URL, for me, it had a profound change on how I was able to collaborate with people in an environment doing software development. Because if you're trying to deal with big data in an ad hoc way, and you don't have a distributed file system, these things which the distributed file system makes simple are these horrible chores that take up all of your time. If you're not working with HDFS or a distributed file system, and you've been asked to do some sort of data processing task, and the data is larger than one machine, I can pretty much guarantee you you're going through the following situation. Somebody on the operational team of your company has to set up more than one machine for you. You're trying to hack together some sort of job that you're giving to that operations guy as a jar file. Then he needs an SH script to start the jar file. Then you go through the permissions problems. And everything in the methodology is ad hoc when you're not using a distributed file system. A friend of mine who was pretty early at Google said that one of the reasons that Google was successful is because they systematically approached these problems and said, what we need is a distributed file system, and when you have those right underpinnings in place, many of the tasks on top of it become much, much easier. So HDFS is really wonderful. I really like it. In terms of its performance, and getting back to the overall description of this talk, it is HDFS real time. HDFS is real time. How real time is an it depends type of problem, because it depends if you're running on SSDs, it depends on the speed of your network. and on and on and on. But HDFS is very much real time. You make a call to HDFS and you're going to get the response coming back typically in a few milliseconds. The robustness of HDFS is also very, very real. You can take machines in and out, and I've never lost data on HDFS, and I've done some dumb things with HDFS, as everybody does when they get started. With great power comes great responsibility. When you have a big distributed file system, you can do a really dumb thing like a Hadoop FS-RM from root, and you can wipe out an entire company. And you might think that's kind of nuts, that would never actually happen. It actually does happen. And in fact, almost everyone you talk to who gets started with a distributed file system has their horror story about how they hadn't gotten around to implementing trash and permissions, and somebody deleted the root of their file system. So you have to be careful. Okay, now if we go to slide 15. Let's talk about some of the motivation for real-time access to Hadoop, which a lot of companies and open source projects are pursuing right now. So big data is more opaque. It's harder to see than small data. Typical ways of getting some answers like pivot tables and spreadsheets, they choke on big data. BI tools don't scale up to big data, and small samples often don't replicate the true nature of your data, especially if your data is fast moving. So engineers, data scientists, and analysts want a faster time to answer on big data. And they want to rapidly be able to find segments, quantify them, and extract them. And they're suffering from what I call the I don't know what I don't know problem. And the farther away you get from engineering, you go from engineering to data scientist to business analyst to CFO level position of a company. The business analyst right now has very, very poor visibility into Hadoop. And he or she has trouble even formulating a question about what's in the data. So it's hard for them to even ask the people in engineering to do extractions of the data for them or to get answers because they're so hard pressed to know what's actually there. So if you can provide a real-time interactive query capability on Hadoop, then you can democratize access to big data because engineering won't have to intervene or, if you will, be bothered at every step in the process by the data scientist and the business analyst. So on slide 16, I get into a survey of what's available right now in real time for Hadoop. Everybody wants this real-time in situ self-service. It's the holy grail for the business analyst. In situ means in place. When you have big data, moving it around is not an easy thing. And so what you want is to be able to, without moving the data out of HDFS or S3 or whatever distributed file system or database you have it in, perform your analysis and get answers. Right now, real-time access is available in HDFS, but on the next slide, we'll get into whether that's useful for the business analyst or whether it's too low level. In the middle of the spectrum, you have things like HBase, which are providing key-value databases. And then at the other end of the spectrum, you have things like Drill, which is emulating Dremel, which is basically a columnar database that Google developed. And those things tend to be proprietary, really hard to get set up and run. And, they're not a part of the Hadoop stack that a typical developer can use right now. They're just too early. Okay, so slide 17, we can look at each of the layers of the stack in terms of its use case, whether it's supported in Hadoop right now and whether it's real time. So with HDFS, we can seek to a particular byte and begin reading bytes in real time. That's really good. but it's not really a question answering system in real time for business analysts. With HBase, we can seek to a particular value by a one-dimensionally indexed key. And that is somewhat like what's available in key value databases, something like Couch or something like that. But what's different about HBase, and in my opinion distinguishes it a little bit, is its integration with Hadoop. So HBase stores its database in HDFS, therefore it is well integrated with MapReduce, because MapReduce can treat HBase directly via its HDFS files, which it can map over, versus having to sort of, get them via a query, which if you think about the asymmetry of a MapReduce job, maybe the mapper has 50 nodes, and then each of those 50 nodes is trying to extract data. If you're trying to extract data from something that's not a distributed system, like you're trying to extract it from a MySQL database or something like that, you're basically going to be doing a denial of service attack onto that database. HBase works around those issues by allowing MapReduce to directly treat its files in HDFS, rather than doing something like making a call over a socket to a database server. MapReduce, the third line here, is for complex questions expressible in code. And it's whatever you want to do. You have to understand your data. You have to figure out whether you can come up with an algorithm expressible in the MapReduce paradigm. And then on top of that, you have Hive and Pig, which sometimes are able to get the job done if you're able to express your need as a SQL query. So Hive and Pig translate SQL queries into MapReduce. So MapReduce is not real time, and we'll get into why. Probably you already have a sense from looking at the map and reduce code and the shuffling and sorting that it's not a real-time system. And the final thing on the real-time spectrum for Hadoop is ad hoc querying. And this means just being able to say something like field 4 is music and field 9 equals DVD. Or it could be a SQL query, but having the answer actually come back right now, within a minute or a few seconds, as opposed to an indeterminate length of time based on how long it takes your MapReduce batch job to run. And one of the main things that's going on this year is the advance of MPP, massively parallel processing architectures, to provide that ad hoc question answering infrastructure. So if we go to slide 18, I think I kind of already said everything to say on this slide, except maybe that HDFS is trying to emulate Google file system, and that Hadoop file system is different than HDFS. The file system API, I should say the API, is pluggable. You can replace HDFS with other file systems, like S3, as long as you have some layer implementing the file system API. So I do a lot of my work on S3, and I use a layer, a library called JetSet, which makes S3 the new file system compatible. An interesting, on slide 19, this is just an interesting anecdote about S3. I like doing a lot of my development using Elastic MapReduce on Amazon and using S3 as my distributed file system. S3 is super scalable. Last year it had almost 1 trillion objects in it. And the only thing better than a distributed file system that has redundancy and allows you to unplug machines and is robust is putting all that inside of a black box as a service. And that's what S3 does. So with S3 and the Jet library, you have a distributed file system. It's robust. It has visual, graphical user interfaces. You can log in through Amazon and list your files, delete your files, do whatever you want to do with them. And you don't ever have to worry about the operational maintenance of that distributed file system. By the way, it's also geographically redundant and does a lot of other things that HDFS doesn't do out of the box. Elastic MapReduce is something I would also encourage everyone to look at if you're considering, how do I get started with MapReduce? if you learn MapReduce programming with Hadoop, everything you learned with that will continue to work with Elastic MapReduce. And what Elastic MapReduce does is start a Hadoop cluster for you on demand to run your MapReduce job. And so you can say, I have this MapReduce job to run, here's my input data in S3, here's where I want the output to go in S3, and I'd like 50 M1 large EC2 instances running Hadoop task lanes. And when the job's done, the cluster will just shut itself down and go away. So there's this paradigm on Amazon where you can do MapReduce and have files in the distributed file system, and you don't ever have to get into the operational maintenance of a distributed file system and Hadoop. That's all done for you by Amazon. And I can't recommend really strongly enough that organizations, especially small ones, startups, take a look at Elastic MapReduce, because for years I built Hadoop clusters myself. You'd have operations guys that would get the servers set up, and invariably there would, a couple times a year, there'd be these problems that we would dig out, and they would be due to things like a single server not having NNTP properly set up, and that causing clock skews in HBase. On Elastic MapReduce, HBase clusters can also be launched on demand. All the configurations are clean. You'll never have any of those problems. Saves and sorry to the operational guys, but it means you don't need them, and you can save a lot of money. Okay, so on slide 20, I'm just considering whether the Hadoop map file can be used as a distributed key value store. Kind of a substitute, a poor man's database, if you will. And I'm going to tell you why it can't be, and many people are tempted to use it. Don't bother. It won't scale up to interactive real-time access, and it's because the map file, index file, needs to be loaded into RAM. So anytime somebody's proposing a mechanism for real-time big data access, and one of the things you have to do is just fit something into RAM, alarm bells should start going off, and you should start thinking, wait, this is a big data problem. Even if it's just an index file, at some point that index file itself becomes big data. So in general, anytime you have an architecture that wants to deal with big data and says just fit this into RAM, you should be kind of scared of that. Doesn't work well. Okay, slide 21. I start to talk a little bit about HBase here, and I see that we're far, far, far from being at the end of the talk, so I probably need to accelerate things as well. So let's see. So HBase is a clone of Bigtable. Bigtable is the next layer that Google built on top of HDFS when they said what we actually need here is a simple database, not a relational database, not necessarily a transactional database, but something that gives us key value access, gives you random access. Because random access, as I was saying earlier, based on anything other than a byte, isn't a seek, a byte offset, isn't practical in HDFS, so you have to build these layers on top of it. And Bigtable is what Google, you guys probably already know this because you're a Google developer group, but Bigtable is where Google basically stored the web that they downloaded and built their search index for. And as I was mentioning earlier, HBase allows you to MapReduce directly over the tables by treating them as files. One of the problems with HBase is that once you've committed to a key design, it's very hard to change that key design. And the other problem with it is you only have one key that you can search on. So there are any number of projects right now. One was just open source called Phoenix the other day that are trying to give you multiple indexes on HBase so that multiple columns and fields in HBase can be indexed. Everybody's trying to get closer to this idea that you can just do a query on any column and yield a result quickly. The problem is that HBase isn't designed for that at all. It's only designed to index a single key. And so the systems that try to index on multiple keys often involve literally copying all of the data and into separate tables, each table having a different key over a different column. I think that's kind of silly, but I guess in some situations it works. Okay, on slide 22, there's an overview of the H-based architecture, which looks pretty complicated, and it is. Perhaps not more complicated than it needs to be, but nevertheless pretty complicated. It has a component called Zookeeper, which is a distributed coordination service. And HBase has a master, and HBase has region servers. And I like HBase, it's really, really good, but it's not as robust and mature as HDFS. And I can, people will debate that. That's just my anecdotal experience. You can go look on the HBase list and see tools that I was submitting back to repair corrupted H files. So especially in situations of resource starvation, HBase becomes very unstable. You can avoid that, I think, by making sure that you don't run HBase on machines that you're also running MapReduce daemons on. Because MapReduce, the Hadoop 2, or Yarn as it's called, is going to do a much better job with resource management. One of the worst things in MapReduce and Hadoop right now is resource management. And it's very easy to consume all of the resources on a machine by having a task node that you've allocated too much RAM to, for example. So if you're running HBase on the same nodes that you're running HDFS data nodes or MapReduce task nodes, you're going to run into problems if and when you inevitably will run out of resources on those boxes as you try to push your jobs. Slide 23 has some information on random read performance of HBase. There are a lot of benchmarks you can go to and look at on the web. I just want to point out that one of the things about HBase is it's not this sort of memory architecture where you're copying all of the data. Your authoritative data is going to be in HDFS. HBase region servers really exist for the purpose of sort of buffering up writes and providing you fast write access so that writes can be sort of committed and merged into the files in HDFS at once, and so that it can survive restarts and so that it has a write log. Except for caching, you're not going to get better read performance out of HBase than you got out of HDFS. Caching can help you, but don't really plan on caching to help you for big data flow. So on the next slide, on slide 24, there are some, there's a histogram of the read times in HBase. Reads are called gets in HBase. And most of the reads are below 100 milliseconds. HBase is a good real-time key value database. And so if we have to talk about if it's real-time, I say yes, it's real-time. Okay. Given that we've been going for an hour here, I think I should probably stop now and take any questions that you guys have.
No, it's silence right now.
Does that represent sort of total confusion, or have I been clear? I don't know.
Me neither.
Please ask me any questions you might have. I'll do my best to try to answer them.
Okay, I can ask a question.
About MapReduce.
I have a question. You showed on the first slides the example of mapper and reducer. It wasn't this for the text word counting. It was even more simpler, yeah?
Let's see. On slide 6.
Yeah.
No, this is actually this is actually the mapper for word count.
Okay.
And so it's receiving a line, it's splitting the line, and for each token in the line, it's emitting the word and the number 1. Which, if you go back to slide 4, you'll see that's what it does. So on slide 4, you have a line token coming in that has the words deer, bear, and river on it. And it splits it into 3 words, deer, bear, and river, and for each one, it emits the key value combination of the word and the number 1.
Okay, and where is the one that splits by spaces, by white space? Like
so they're using the string tokenizer to split the line here on slide 6. And then they're asking it, tokenizer has more tokens for each token. They're setting the token value into the writable text word, and they're emitting that static value of 1.
Okay.
So yeah, I mean, that is one of the cool things. I mean, one of the great things about MapReduce is that you don't have to, it's a push model where it pushes the pieces of the file into your code, and you do not have to get into the weeds of, finding the file, splitting it up. It does all that for you.
Okay.
Good question.
I have one more question. If this is a push model, then we can compare it to the XML parsing, whereas it's usually, if you use a SAX parser, you get events pushed into of the nodes. So, but this is not always convenient. Is there a way to use a pull model for this?
That's an interesting question. Take a step back and consider that when you're dealing with MapReduce, the files and the sizes of the files that you're dealing with are much, much larger than, they could be much larger than you could even fit on the hard drive of a single machine, right? Like if the files here are, all of Google Books, for example, you wouldn't want to run that through a parser on one machine, okay? And so what MapReduce is going to do is, it's going to take the file in the distributed file system, it could be a terabyte in size. It's going to split it into configurable split sizes. You can, if you want to get into that, you can tell Hadoop how big the splits are, okay? They could be 16 megabytes, they could be a gigabyte. And then Hadoop is going to manage going through each of those records and pushing them into your job. Hadoop doesn't do a good job at XML parsing. That's actually one of the places where it has unbelievably bad support. One of the workarounds for that is to create pseudo XML files that encode XML onto a single line without pretty printing it, and to use the text input format to represent those pseudo XML records on a single line. If you don't do that, Hadoop has a very, very difficult time finding where one XML element ends and another begins, and some of that depends on your XML data model. So, XML parsing, dealing with, gigantic XML files is a troublesome thing for Hadoop. Instead of using XML and worrying about parsing, one of the things you can do with Hadoop is to use the built-in file formats. And typically, once you get going with programming on Hadoop, you'll get comfortable generating files that are sequence files, Hadoop sequence files, that have keys and objects expressed in your domain model that are serialized as binaries by Hadoop. Once you do that, then you're sort of working within a model that Hadoop is very good at dealing with. So, a lot of times what you'll do is a pre-processing job, which will actually take your XML and convert it into a file format that Hadoop is better at dealing with. So there's no direct comparison to SAX and DOM parsing, is the short answer. It's just a different animal.
Okay, thank you.
Is someone asking a question? I can't hear, sorry.
No, nobody's asking, I think, right now.
Okay.
So on which slide are we?
Well, I mean, I think, you know, given, I mean, Arthur, tell me if you feel we have more time, but I was thinking, given the hour, that we're not going to be able to finish the whole presentation.
Yeah, I see. If you have some
enough material that we should stop now.
Maybe if you have something quick to show that is urgent, because our next speaker is waiting.
No, let's wrap up.
What do you think?
I think we should finish and give the next speaker his airtime.
Okay.
So thank you very much.
Thanks.